Welcome back to my course on Fundamentals of Electrical Engineering. We were on frequency response in the third section on in-control systems, and we had touched upon some problems that are mostly to do with frequency. But now we go into the heart of frequency response when we examine Bode plot. Okay, so Bode plot is a beautiful representation of the system because most of its inherent characteristics become clear if we examine Bode plot. So this is the route that we are going to take while we examine the gate problems which use Bode plot as such. Okay, so let's look at the first problem. So most of the theory that I have refrained from speaking will be spoken of as we examine the Bode plot. In fact, if you learn Bode plot, you are of course some problems in Nyquist or polar plot also come, but at the same time Bode plot happens to be more popular in gate examination contest. So let's look at this particular problem. As usual, let's look at the diagram. What do you see? You see two concepts of Bode plot put together. What does it mean? So I would say that you can look at the phase angle, angle GG omega shown there, and we see that it goes from 0 to minus 180 degrees. Okay, so this should immediately bring to your mind that there are two poles. Okay, that's okay, two poles, because two poles will contribute to a total of the poles will contribute to a total of minus 180 degrees. But are we right? No, we are not right. Why? Because the magnitude remains constant, and magnitude can remain constant only if there's a zero, it's also a pole, and they are at the same frequency. Because we have seen this before, square root of omega square plus alpha square should be equal to square root of omega square plus again alpha square. One of them may be positive and other must be negative. That is true too, because we want to have a minus 180 degrees, so the numerator should also contribute to a minus 90 degrees. Okay, so in that sense we see that there's a zero, okay, and there's a pole, and for a zero to get a negative angle it has to be on the right hand side, whereas the pole should be maybe on the left hand side. Let's see the Bode magnitude of plot of a first order stable system. So stable system means that the pole is always going to be on the left hand side of the S plane. It's constant is what we saw right now with frequency. The asymptotic value of the high frequency phase for the system is minus 180 degrees. This system has one pole. We already guessed it, one pole which is stable, so it has to have it will be located on the left hand side of the RHS plane of the S plane, and it will need a zero, but it will be located on the right hand side of the S plane. I suppose both aspects are clear. In fact, we talked about three concepts. One is that check out the angle. Okay, we see minus 180 degrees. Do we see two poles? No, we don't, because the magnitude remains the same, which means that both the pole and the zero must be at the same frequency. Okay, so that's fine. Then we move on to what is called as, okay, is it stable? Okay, if it is stable, it is the pole which has to be on the left hand side. Okay, and the right hand side the zero has to contribute a negative angle, which is possible only if it has a zero on the right hand side of S plane. Okay, so let's go to the second problem. This is also very simple. Okay, the fact of the matter is that you must first and foremost think that the problems in Bode plot happen to be simple. Okay, so what do we have here? We have a circuit with a resistor, inductor, and a capacitor, and Vi and Vo are shown. The input and the output voltage are shown. We are also given a Bode plot which is more or less constant, except that it peaks at omega is equal to 2000 radians per second, okay, or omega is equal to, okay. So now what is asked is the Bode magnitude plot for the transfer function VOS by VIS of the circuit is as shown. The value of R is what? Okay, so yeah, so now what do? We find out VOS by VIS and then draw. Okay, think in terms of its frequency response. So what is VOS by VIS? We have done it before. 1 by CS divided by R plus SL plus 1 by CS, and then take the S downwards such that we have S square L take out L, okay, such that you get S square plus eta omega ns plus omega n square. This is the style we want, and we are achieving the same thing by realizing that C 1 by Cs is the same as equal to 4000 by S. So 4000 by S is divided by R plus S into 10 raised to minus 3, which is the Henry value of the inductor, plus again 1 by Cs. Okay, take the S down, also take out 10 raised to minus 3. So we have 4 into 10 raised to 6 on the numerator because of 10 minus 3 going upward, and we have S square plus 10 raised to 3 Rs plus 4 into 10 raised to 6. So now it has come to that particular format of omega n square divided by S square plus 2 eta omega ns plus omega n square. So now we are ready for setting S as equal to do we want to have the peak value? So let's set S equal to j omega, where omega is equal to 2000. Okay, so now it becomes very simple. We see that S square becomes, okay, always S square will be negative. Okay, same concepts that we have been talking about. So it becomes negative because j square is negative, and that's equal to 2000 square, or 4 into 10 raised to minus 6. So omega n square, and this cancel. Okay, so now we are left with, on the denominator, only 10 raised to 3 R into j, of course, and omega, which is equal to 2000. So what we have there, 10 raised to 6 and 10 raised to 6 cancel, and 4 by 2 gives us 2. So if you take the log magnitude of V naught S by VIS, which is what we have seen, it's the same as equal to 20 log 2 from the numerator, minus 20 log R, because log R is alone left in the denominator, is equal to 26 dB, because that is the peak value. And 20 log 2, it's always the 3 dB point, so we have it's the same as equal to 6. So deduct 6 from 26, that is 20. So minus 20 log R is equal to 20. What does it mean? Log R is equal to minus 1. And when you have R as equal to minus 1, the log 10 is equal to 1, log 1 is equal to 0, and log 0.1 is equal to minus 1. Okay, so we see that R is equal to 0.1, and from the answers it's very clear that A is going to be the correct option. This is a very simple problem. The only because it looks big, people don't do such problems, but it's very simple. The only point that you have to notice is that 26 dB is the peak value of V naught S by VIS, and it occurs at omega is equal to 2000. Okay, so 26 dB has to be equated to whatever happens to V naught S by VIS when you give its frequency equivalent, where frequency is equal to 2000. Okay, so this is the way. These are two theoretical components that I have talked about in this. Okay, so let's move to the third problem, and some of the theory that you can carry with you very easily and do problems based on that. So what do we have there? A symptotic Bode magnitude plot for minimum phase. So what do you mean by minimum phase? That none of the zeros nor the poles happen to be on the right hand side of the S plane. Transfer function GS is shown below. Okay, so let's start from the very beginning. What do you see? It's a descent with respect to with a descent given by minus 20 dB per decade. That means that there's a pole on the denominator. So we have counted out the first pole, and then from minus 20 another descent happens, which is again only of minus 20. Okay, so the totality is minus 40. So it can, this kind of Bode plot can generate only the second pole. So we are having the second pole there, and then it proceeds. It passes through 10. Omega is equal to 10. Where the magnitude is going to be equal to 0. That's also an interesting point, which we'll be covering soon enough. And then we move on to the third section of the log magnitude curve of the Bode plot, where we see that another drop in the slope is happening, and the drop is going to be minus 20 dB per decade, such that the totality is going to be minus 60 dB per decade. So what do we have there? We have 3 poles. Okay, so that's very clear. Yeah, so now we have no zeros. Why don't we have any zeros? Because at none of the points the slope has moved upward. Okay, so statement 1, which consider the following two statements. Statement 1, transfer function GS has 3 poles and 1 0. It's wrong, no doubt about it. Okay. Statement 2, at very high frequencies, omega tends to infinity. The phase angle of GG omega is equal to how many will be there? 1, 2, 3. So each of these poles contribute to minus pi by 2. So because they are on the denominator. So pi by 2 into 3 or minus 3 pi by 2. So statement 2 is right. And that's exactly what we are supposed to find out. And that's B. That is statement 1 is false and statement 2 is true. I suppose this is clear. So in this session, we have tried to locate read the Bode plot to obtain the poles and zeros if there are any. Okay, but at the same time we have not looked at the magnitude, which is what we are going to look soon enough. Okay, so here again we are given a Bode plot. Yeah, consider the following asymptotic Bode plot. What do we see here? Right at the beginning, there is an upward movement for the or upward slope. Okay, so we are going to have a 0. Okay, so because it's upward, it's 0. It's on the numerator. If it's downward, it's on the denominator. So we are having a pole. Okay, so and it's a pole it's a 0 at s is equal to 0. Okay, so that's the first point. And then it levels off. Why does it level off? Because a pole has occurred at what frequency? The frequency is a little above 0.5. Okay, so we'll go into that soon enough. And then again, what happens is that after leveling off, we are going to have two poles. Why? Because the frequency has the Bode plot has steeply gone down to minus 40 dB per decade, or there are two poles. Okay? So how many poles do we have? We have two poles, 2 plus 1, 3 poles, and 1 0. Okay, and S happens to be on the numerator. So from amongst A, B, C, D, we see that B is not applicable. So we reject B. So A, C, D. Okay, so let's see. So we see that there are 3 poles. And one has a multiplicity of 2. Why? Because abruptly the slope has descended to minus 40 dB per decade. Okay, so let's again see. We have 2 poles. Any pole with multiplicity 2, A has a pole at omega is equal to 1 by 0.25, or T is equal to 0.25. Okay, so that's the second part that we are going to look into. So that's okay. And there's also another pole which has no multiplicity. Okay, B was already rejected, C is now rejected, and D seems appropriate. It has S on the numerator, and it also has a multiplicity. But here omega happens to be equal to 1 by 4, or T happens to be equal to 4. Okay, and now we see. Okay, so and of course, we also see that the other pole has a frequency as given by 1 by 2 in option P. Okay, so now let's go further. So 3 poles, 1 of multiplicity, and where does it happen? It happens at an omega less than 8. Okay, if it happens to be at an omega less than 8, it means that the time has to be, because it is 1 by 8, time has to be a little more than 0.125. So we see that and at omega greater than 0.5, because we see the descent of the initial slope happening, or the cancellation of the initial slope happening at an omega a little larger than 0.5. Okay, according to a Bode plot, which means that the time has to be a little less than t. Okay, so all these things all that we saw is true about A only, because we saw that T is equal to 2 and 4 in this case, which cannot be true, because T has to be more than 0.125 in one case and less than 2, which has been violated in D. So that's all that's there. Now we can also look for the magnitude. Okay, if this is true, now we just need to look at the magnitude if required. We don't need to look into that, because we have already rejected all of them except A. Okay, but at the same time, to look at the magnitude, one way of looking at the magnitude is to equate 20 log k, that is the initial portion, as equal to minus 20 log 0.5. Why? Because the Bode plot is cutting in the initial portion. The Bode plot is cutting when only S was there, that is the 0 was there, was cutting the frequency line at omega is equal to 0.5. Okay, so you see that 20 log k is equal to, so 20 log k, this is the general pattern. It should have been 20 log k plus 20 log 0.5 is equal to 0. Okay, so 20 log k is equal to minus 20 log 0.5. So you take the logarithm of 0.5, which is again minus 0.3010, because 0.5 is the same is equal to 1 by 2. Okay, so minus 20 into 0.00 is equal to, it tells us that k is equal to 2. Okay, so if k is equal to 2 in this particular format, so please watch out for the format. What is the format? That is, on the numerator you have k, on the denominator and in both in poles and zeros you will have what is called as a structure which will be equal to, which will be like 1 plus st. Okay, it should be 1 plus st. T, of course, is having a dimension which is reciprocal to the dimension of frequency. Okay, so you cannot say something, you cannot have in this particular way of assessing k, you cannot have s plus 10 etc, because 10 needs to be taken out and then it has to be 1 plus s by 10. Okay, I hope this is clear. So as we do more problems, it will be very clear to you. So let's go to the next problem, which is just developing our concepts a little further. So 3 or 4 concepts were discussed. One of the main points that we got here happens to be that 20 log k minus 20 log omega is equal to 0 if the initial portion of the Bode plot cuts omega axis at the cuts omega axis, or the gain is equal to 0. Okay. Okay, so now let's move on to the 5th problem. We again have a log magnitude curve, or what may be called as a Bode plot. Okay, and we see that it plunges from plus 20 to minus 20, but then the plunging starts off at 1 and ends at 1k. Okay, it starts off at 10, the frequency of 10 hertz, and it stops at and then it stops at 1k, and in between you are having 10 you are having a frequency of 100 wherein it becomes 0. Okay, so now we have many things here. We see that a decade is given by the frequency has been, the frequency line or the axis has been drawn based on a log magnitude curve. So we are having 0.1 into 10 is equal to 1, 1 into 10 is 10, 10 into 10, 100, okay, and so on and so forth. Okay, so we are having a decade as the what are the markings on the frequency axis. Okay, so definitely it has come to 0 at, that is the amplitude or the magnitude has come to 0 at omega is equal to 100. Okay, so the curve can be called as 20 dB per decade, and of course it is descending, so minus 20 dB per decade. So that's the first thing that we notice. Again, let's treat the problem. A Bode magnitude plot for the transfer function gs. A plant is shown in the figure. Which one of the following transfer functions best describes the plant? Okay, so now let's start picking. What happens is that there is no plunging in the beginning, it is steady, so you have neither s on the numerator or the denominator, or in other words, you don't have a pole or 0 at s equal to 0. Okay, so that's clear. Why? Because there is no slope at the beginning. Okay, only at 10 you're going to have a descent. So 10 happens to be a descent, which means that at omega equal to omega equivalent to 10, we are going to have what may be called as a pole. Okay, setting off the Bode plot with the negative slope of minus 20 dB per decade. So there's a pole at s is equal to 10, or s plus 10 is acceptable in this case. Okay. Thereafter, the minus 20 dB per decade descent is offset by a 0, and that happens at omega is equal to 1000 or 1k, omega equivalent to 1000 because it's given in hertz. So we can say that you will have on the numerator s plus 1000. Okay. On the other hand, it's possible that you can have the whole construct can be the same as equal to 1 plus s by 1000 and 1 by s plus 10. There is neither a s on the numerator or on the denominator, and that's the reason why b and c are automatically rejected. Okay, so at the other two, let's contend between the two. We have on the pole. We have on the numerator a 0 is given by omega is equal to 10 and a pole at omega is equal to 1000. Everything is fine, okay, except for the magnitude. So how do we look at the magnitude? Okay, so 20 log k okay, is equal to, now we are looking at a different picture altogether. Okay, so what is going to be the frequency at the beginning? Okay, or the log magnitude at omega equal to 10 is the same as equal to 20. So 20 log k is equal to 20. Okay, so that so which means that at omega equal to 1. Okay, so omega equal to 1 happens to be very important by when you take the log value of 1, it's going to be equal to 0. Okay, that's why you say that 20 log k minus 20 log 0 or 20 log 1, which is equal to 0, is equal to 20. Okay, so obviously k is this happens at k equal to 10. Okay, because because logarithm of 10 is equal to 1. Okay, so those things must be with you. Okay, so which means that k should be equal to 10. Okay, so now let's look at the format. If you take out, okay, let's look at 1000 here. The format tells us that it should be for k to be equal to 10, you should take out 10. Okay, and you should also take out 1000. Okay, so you will have what is called as you'll have then you will have a particular kind of appearance. And on the other hand, if you take out if you so you will have so let's take d. D tells us that if you take out 1000 from the numerator, okay, so that's there, and then if you take out 10 there, so 1000 by 100 you get k equal to so k equal to 10 in should be the value, and k equal to 10 is happening also in option D. So we go for option D. Okay, so let's go to the next problem. Okay, again, it looks complex, but it's very simple. Let's see. We are having a Bode magnitude plot of the transfer function GS. The transfer function is given as k into 1 plus, the format is correct. Yes, k into 1 plus 0.5 s. So T1 happens to be 0.5, 1 plus AS. Now we have an unknown A. And then on the denominator, or the poles are, there's a simple pole at S is equal to 0. So we have S. We are having 1 plus S by 8, 1 plus BS, another unknown, 1 plus S by 36. Okay, so we have several frequencies. The first one happens to be at 1 by 2 because it's given as 0.5. That's the pole, that's the 0. And then we are having another one at 1 by A. And we have having one at 8, another at 1 by B. And these are the poles in addition to a pole at S is equal to 0. Okay, and we also have, okay, so now let's follow the diagram. We see that corresponding to the pole S at the pole, a simple pole at the origin, we are having a descent of minus 6 dB per decade, which is the same as equal to 20 dB per decade, okay? Minus 20 dB per decade. Okay? And what is required is the value of A by BK. Okay, this is what is required. Okay? So minus 6 dB per decade would have proceeded, except for the fact that 0 has come about, and it cancels the slope of minus 20 dB per decade or 6 dB per decade octave by a 0 at omega equal to 2. Okay, so omega equal to 2 is already accounted for as the first term in the numerator. Okay, then we are having then after leveling off the Bode plot, now it starts to move upward. What does it mean? Another 0 has originated at omega equal to 4. So now we see that A is the same as equal to the 1 by omega. So A is equal to 1 by 4. I suppose this is clear, okay, because A is written as the coefficient of S, which means that it has a unit of time. Okay, so now A has been resolved as equal to 1 by 4. Okay, so now so once frequency 8 is reached, or omega is equal to 8 is reached, what happens is that now again we are having what is called as a leveling off of the upward slope, or we are going to have the next pole. The first pole was at S is equal to 0. Okay, was at the origin. Okay, so now we see that again we are having that is 6 dB per decade or 20 dB per decade has been leveled off. Okay, so we have only one simple pole, and that happens to be at omega equal to 8. Okay, so now do we have that? Yes, the second term in the denominator is 1 plus S by 8, so that's taken care of. The next one happens to be, again, after the leveling off, we are going to have a downward slope of minus 6 dB per decade at 24. Okay, or in other words, B is in time unit. So 1 by B, or B is equal, or omega at which it happens, or B is equal to 1 by 24. Okay, so B is equal to 1 by 24, and A is equal to 1 by 4 is already accounted for. Okay, so now we need to find out only K such that A by BK can be found out. Okay, so now let's look at the magnitude version. Okay, so if we had what is called as, if we had if we had 20 log K, okay, minus 20 log 2 would have proceeded. It would have 20 log K at frequency 2. What would be the, let's see what would be the dB value. Okay, so if it had proceeded, okay, so minus 6 dB decay, which was the earliest slope, if it had proceeded as is shown in the diagram, it would have reached the frequency axis at omega is equal to 8. The gain would have been equal to 0 there. Okay, so this is what we are saying. We are saying that the value, the gain would have reached 0 at omega is equal to 8. Okay, and an octave means that at frequency 4, it would be because it's a 6 dB per octave kind of slope, and octave means half the frequency. So at 4, it would be 6 dB. I suppose this is clear. This is just the law of triangles. Okay, so 4 by 2 is 2. So frequency at the dB value at 2 would have been 12 dB. Okay, so if 8 is 0, 4 would have 8 has a gain equal to 0. 4 would have the frequency at frequency 4 omega. 4 at omega is equal to 4, we would have a gain as equal to 6 dB, because 6 dB is the descent per octave. Okay, then at half this frequency, that is half of 4, or at omega equal to 2, we would have 12 dB as the gain at omega equal to 0. Okay, so, and we are supposed to take the log magnitude curve or the gain only in the initial portion. That's why we have arrived at omega equal to 2 with the gain as equal to 12 as being governed by as being influenced by the initial slope, which is of minus 60 dB per decade or 20 dB per decade. Okay, so now we see that 20 log K, which is the initial portion, minus 20 log 2. Why? Because it is pole. So it is associated with the pole, and that's equal to 12 dB. So the gain at omega equal to 2 is equal to 12 dB, and it's given by K by S. Okay, so that's the reason why 20 log K minus 20 log 2, where S is equal to omega and omega equal to 2 is equal to 12 dB. Okay, so now we can easily, we know that again 20 log 2 is equal to 6 dB. So we have, so we can see that 20 log K, 6 has been, the absolute value has been taken as 6.02. So 20 log K is equal to 6 dB. So now we see that, so K can be assessed easily as equal to near around 8. Okay, so now A by B by K is the same as equal to 0.754, and from amongst the different options you can choose for B is equal to 0.76. Okay, I hope this is clear. So 20 log K is equal to 6. You can directly take as equal to, you can actually, you need not go through all the additional details that are given in the slide, but then you can, I suppose you can even, you can take the anti-log and you can find out. Okay, let's go to the 7th problem here. What do we have here? Again, a Bode plot with the descent of minus 40 dB per decade. Why? Because it's going from 32 to minus 8. Okay, so Bode plot of a transfer function GS is shown in the figure below. The gain 20 log GS is 32 dB, and minus 8 dB at 1 radians and 10 radians respectively. Okay, so it's showing a the frequency. There's a decay between 1 and 10. Okay, so in a decay, the magnitude falls from 32 to minus 8. So the total fall is minus 40 dB, and that happens in a decade. So we have already assessed the shape of the log magnitude curve. Okay, yeah. So now what do we have? Yeah. So we also see that okay, there is a frequency of a frequency of 1. Okay, wherein the magnitude happens to be 32. So 20 log k is equal to 32. Okay, because 20 log k minus 20 log 1, which is 0, because that's the frequency. Okay, so and it is k by s square. So we see that so 20 log k minus 2 into log omega, where omega is equal to 1. So even the 2 does not have, because log 1 is equal to 0. So 20 log k is equal to 32. Okay, so this is the same pattern that we have been using all along. If you have the decibel value at any point, at any frequency, you can use that, so long as the initial slope is maintained. Okay, so you see that now we have 20 log k is equal to 32. So log k is equal to 32 by 20, or k is equal to 10 raised to 1.6. Okay, and what is asked is, the phase is negative for all, then GSS is what? Okay, so of course since the slope is minus 40 dB per decade, we are having an s square on the denominator, and we also see that k is equal to 10 raised to 1.6. So 10 raised to 1.6 is near around 10 raised to 2. So we can solve any of the values which are near to that. Okay, you can always calculate 10 raised to 1.6, or in other words, you can see any value if any gain happens to be near around 10 raised to 2, you can opt for that. So two values are there, 39.8 and 39.8. The other value is 32, which is a little too low, but at the same time we need to have a square on the denominator such that the initial slope can be minus 40 dB per decade. Okay, so we see that option B is correct. Okay. Let's move to the eighth problem. Okay, so asymptotic approximation of log magnitude versus frequency plot of a system containing only real poles and zeros is shown. Its transfer function is what? Okay, so now we see that in the initial portion at omega is equal to 0.1, we are having 80 dB. So that can be utilized. Okay, but what is the slope there? It's minus 40 dB per decade. So you have to have what is called as s square on the denominator. So option B and option C tells us that s square is there. Okay, so step by step we are proceeding, and then we are going to have minus 60 dB per decade starting at omega equal to 2. So we are going to have another pole there. Okay, from minus 40 to, okay, but at omega equal to 5, the slope is again moving on to minus 40 dB per decade. So another 0 is emerging at omega is equal to 5. Okay, then we move on to the next portion, wherein at omega to 25, again there's a deeper descent to minus 60 dB per decade. So a pole comes into the picture. So how many poles? We are having a multiplicity of poles at s is equal to 0. So s square should be there, and then you're going to have two more poles, because there is from minus 40 to minus 60, and then again from minus 40 to minus 60. So two poles, and we also have only one 0, because the slope ascends to minus 40 dB only at s is equal to 5. Okay, at s is equal to at s is equal to 5. Okay, so so that's it. So we see that we are having, we should have s plus 5 by s square and s plus 2 and s plus 25. Okay, so now let's look at the k value. Okay, from a particular format, please opt for 20 log k minus 40 log 0.1 is equal to 80 dB. Why do we get 20 log k? Because that's always the pattern. Minus s square, because k by s square is taken as equal to having a magnitude at s omega is equal to 0.1 is equal to 80 dB. That's the reason why 20 log k minus 2 times 20, that is 40 log of 0.1 is equal to 80 dB. Okay, so we solve for that, and we see that k is equal to 100. Okay, so now to get k as equal to 100, from the different options you can take out 5, 2 and 25. So these are the values that we saw in D and D. And if you multiply that by 1000 in the first case and 80 in the next case, you should get what is called as k equal to 100. Okay. So option B is more correct. I suppose you first estimate that value and then from the different options, see what you have to get. Okay. And if they match, you go for that option. Okay. I suppose this is the pattern that we have been following. You can have your own pattern so long as you understand that the format of 20 log k minus 20 or 40 or 60 or whatever, keep minus because of the pole. If it is a 0, it will be plus. Okay, and then if you are having multiplicity, 20 will be multiplied accordingly, and then you will have logarithm at a particular frequency as equal to the decibel value at that particular frequency. Okay, so that's all that's there. If you can remember that, you will be fine. Moving to the ninth problem. Asymptotic Bode magnitude plot of a minimum phase transfer function. Okay, minimum phase means, so I think it was mentioned before, both the numerator and the denominator will have poles on the left hand side of the S plane only. Okay, is shown in the figure. So initially we start off with minus 40 dB per decade, which means that there are 2 poles. Okay, and then you are going to have minus 20. So one more 0 has arrived, and then we are going to, and even this minus 20 dB is going to be it's going to be leveled off at another frequency. The frequency values are not given, but then we see that in that sense we are having 2 poles and 2 zeros. Okay, and so that's what is asked. This transfer function has how many poles and how many zeros. So option C is a direct kind of answer to this particular problem. Okay, now let's move to the 10th one. H omega is given as 10 raised to 4 and 1 plus g omega. This is the pattern that we've been. No, this is not the pattern. This is 1 plus g omega. So it's given in frequency. Okay, 1 plus g omega. So there is a 0 at omega equal to 1. Okay, and the next is that there are 2 poles. One is at omega equal to 10, another is at omega equal to. So now the dimensional compatibility needs to be abided by all the time. Okay, so at 100. Okay, and when you take the logarithm at 1, it's 0. At omega equal to 10, it's going to be 1. And omega equal to 2, omega equal to 100, it's going to be 2. And that has multiplicity. Okay, so now which is the correct Bode plot is what is asked. Okay, so what do you see? Yeah, so initially at omega equal to 0, you have the 0 working out towards a positive slope. Okay, so, or a slope moving upward. Okay, so this is true only for case A. Okay, in all other cases the slope is moving downward at omega equal to 0. Okay, at omega equal to 1. Okay, wherein log omega becomes equal to 0. Okay, so without doubt you pick out answer A. So all the other aspects match. So answer A is the best that we can do in these circumstances. Okay, so last slide and last problem. The system having a Bode magnitude plot shown in figure below has the transfer function. Okay, so this is the most recurring kind of problem. So there are 2 aspects: how many poles are there, how many zeros are there, where do they occur, based on the slope of the Bode magnitude plot, and looking at that particular format. Okay, where we are having k into 1 plus s t1 or 1 plus s t2 etc. on the numerator, divided by s square or s or whatever, either on the numerator or the denominator, 1 plus s again t4, 1 plus s t5 etc. Okay, so this is the pattern that we need to have if we are going to take 20 log k as equal to 20 log k at the initial value, at the initial slope, which is having a downward slope or the pole. So minus 20 log 0.01 as equal to 60. Okay, so this is something that we need to remember. So let's look at the number of poles and zeros. Definitely we start off with a pole on the pole at omega equal to 0. At a pole at s is equal to 0. So we have B, C, D answer to that. Then we are having the next, again, the second pole at omega equal to 0.05, or t is equal to 1 by 0.05, it's the same as equal to 20. So answer B answers to that. Okay, and s plus 0.05 is also true, that the D is also right. And then we see that the slope now moves upward. We are going to have a 0 at omega is equal to 0.1. Okay, that's answer D. And on the other hand, T is equal to 1 by zero point 0.1, that's equal to 10. So answer B is also right. Okay, now to look at the slope value, as we saw, as the magnitude value, as we saw. Okay, so both answers seem to be right except for the magnitude. Okay, so let's see what the magnitude is going to be. So we have 20 log 20 log K minus 20 by minus, because s is on the denominator, minus 20 log 0.01 as equal to 60. Okay, so if you solve that, you can see that it is the same as equal to 10. So answer B is right. Okay, so from on the other hand, if you pick out all the omega values from the from answer D, you see that 5 into 0.1 divided by 0.05 is also equal to, that is taking out all the omega values. Okay, so you see that again it's also going to be equal to 10. Okay, so both B and D happen to be true. This is an unfortunate circumstance. Perhaps you'll get marks for both the answers. Though in GATE examinations, I noticed that the problems are almost always perfectly given. Very rare mistakes are there. But I hope some of the concepts that were relayed in the session are very clear to you. First and foremost, what does the Bode plot give you? It gives you a magnitude understanding and also a phase angle understanding. Okay? The most important first point needs to be to find out how many poles or zeros are there in the at s is equal to 0 at the origin. So that will be given by the initial slope. If the slope is not, if there's no slope and if the slope is equal to constant, then you say that you are having there is a the Bode plot happens to be on level with omega equal to 0 axis, then you say that omega equal to omega axis, then you say that you are having what is called as neither poles nor zeros on the origin. Okay, then you move on to the different poles and zeros that are there as reflected by the Bode plot, shifting its slope from one to another. Okay, so once that is done, there are two ways of representation. One is as s plus omega. Okay, and other is as 1 plus s by omega, or 1 plus st. Okay, so these things need to be taken into consideration. Finally, 20 log k minus, okay, if there is a pole on the if there is no pole or zero at the origin, then 20 log k will be the magnitude at a particular value. A very important point happens to be when omega equal to 1, because 20 log 1 is equal to 0. Okay, so there are different possibilities. The different possibilities have been discussed. Let me hope that I can also consolidate all of them in the final slide. Thank you.